All right, let's start off with a do now. So what qualitative and quantitative information is given by the following examples? Remember that qualitative is basically a quality. So just in this case, what is there? We can't see this stuff. We can't measure it. So we really don't know what it looks like, what maybe it, how big it is, taste, nothing should taste chemicals, but taste or appearance. So really we just want to say what's actually there. So for this one, we know that there is copper, we know there's sulfur, and we know there's oxygen. And that's really all we can say. We don't know anything about it. We can't see it or anything. For this one over here, we know that there's hydrogen, and we know that there's some amount of oxygen. In terms of quantitative information, remember it's quantitative like quantity, so just how many things are there. So in this case, how many carbons are there? Sorry, not carbon, copper. How many coppers are there? On the left, we see no number after the copper, so that would just be a 1 if anything was there, so it's just 1 copper. For sulfur, this is the same thing. There's no number, so it's as if there was just a 1, and we know there's just 1 sulfur in that molecule. For oxygen now, we actually see a number. There's a little 4. So we now know that there are 4 oxygens in this molecule. On the one on the right, we see that in each H2O molecule, a little 2 is there. So there will be 2 hydrogens in each molecule of water. However, because we have this big 5 in front, we know we can multiply these two numbers so that altogether they're going to be 5 times 2 equals 10 hydrogens. Each water molecule has 2 hydrogens. Because there are 5 water molecules total, there are 10 hydrogens in all. For oxygen, it's the same thing. There's no number next to oxygen, so we know there's only 1 oxygen in each water molecule. But because of this 5, our 5 water molecules altogether give us 5 times 1 equals a total of 5 oxygen molecules. Sorry, oxygen atoms. Before we get to the actual lesson here, I want to preface it by saying that going forward, this chapter is going to be kind of like an SAT prep class. It's going to be mostly low-level math, as we've done already, just how many oxygens, how many hydrogens, counting small numbers, adding them up if there's multiple amounts of the molecule, things like that, as well as some verbal skills. So, like I said, how many atoms of this element are in that molecule? How many atoms of that element are in the molecule? What is the basic ratio, as we saw in class yesterday? How many of these things compared to the other guy are there? And then what do we actually call the molecule we end up with? So you saw yesterday something like, I think it was aluminum oxide and sodium chloride. How did the name change? What do you notice about the name? Things like that. It's really not a lot to go through. It's just going to have very simple kind of set rules. You do the exact same thing every time, always follow it the same way, and you always have your reference table, as always, to help you out with it. So now let's start by taking a look at some fractions. We talked a little bit about this yesterday, and we did the formulas, Pogel. What do you notice about these numbers? Does anything jump out at you at first? I'm not going to actually play the Jeopardy theme the whole way because it goes on for, I think, 30 seconds. That would be, let's check the timestamp. It's actually 39 seconds, so we're definitely not going to play the whole Jeopardy theme. But as you're thinking, hopefully you look at this and notice that all of them have a number on the top of the fraction that's exactly half of the number on the bottom of the fraction. So that's to say the numerator is half of the denominator. The 2 up here is exactly half of the 4. The 5 here is exactly half of the 10. Those are terrible arrows as I'm trying to draw on my tablet, but you get the point. The 19 here is exactly half of the 38, and the 712 is exactly half of the 1424. So if we want to reduce these fractions, we could try to find a common number that goes into both of them. And in that situation, just always try first to use the numbers that you're given, because a lot of time it will be that easy. So in this case, the 2 also goes into the 4. The 5 goes into itself and also goes into the 10. The 19 obviously goes into itself and goes into 38 also. The 712 can go into itself and can go into the 1424. So you don't need to be able to do this in your head. You have a calculator if you need to use it. But most of the time you'll see much simpler numbers like this, like the 2, the 4, and 5 and 10, that you can just go through and hopefully recognize visually before you have to really do any kind of big math. The point here, though, is that they all can be reduced to 1/2. The top number is always exactly half of the bottom number. They can all be reduced. You can take out similar numbers. You can say, take out the 2 out of itself, take 2 out of 4. Take 5 out of itself, take 5 out of 10. And you always end up with 1/2. These numbers always look a little bit different, but they show the same kind of relationship. They always show you that this common relationship of having half of the number on top be whatever the number on bottom is. And that's really all we care about sometimes. We don't always care what our actual number is. If we were looking at these numbers here and saying, well, it's a class of 4 students and 2 of them are male, or it's a class of 10 students and 5 of them are male, or it's a giant college class in a lecture hall somewhere, a giant university with somehow 1,424 students and 712 of those students are male. It really doesn't matter. I mean, those numbers all look very different, but they all have one thing in common, and that's that they have the same kind of relationship, the same 1-to-2 ratio, the same 1/2 relationship that we really care about. And like I said, sometimes that's really all we want to know. What is the basic ratio of some kind of parts? When I'm talking about simplifying fractions and common denominators and things like that, it's the same basic thing with these formulas here. Notice that every single one of them is made up of some number of carbons and some number of H's. More specifically, the number of H's is always 4 times as many as the number of carbons. So in this first one here, we see there's 1 carbon and 4 H's. There's 4 times as many H's as there are C's. The second one, we add another carbon, and we have 2 of them, but we also added 4 additional hydrogens, so it's 8 compared to 2. And the same ratio goes up. Whether it's 3 carbons, 12 hydrogens, 5 carbons, 20 hydrogens, 7,000 carbons, 28,000 hydrogens, anywhere on into infinity. So like down here, whatever the number of carbons is, we're always going to have 4 times as many hydrogens. That's the only thing we really care about. These could represent molecules in nature. We could take those little model kits I have in the front of the room with the ball and sticks and make any of these things. It'd be a lot easier to make one with 1 carbon, a little black ball, and 4 hydrogens, little red balls or something like that, than if I was going to try to make them with 7,000 carbons and 28,000 hydrogens. But we could do it. And it's going to go on and on to infinity. We could take any number of carbons that we can come up with. As long as we had 4 times that number of hydrogens, it would be the same kind of thing, would show the same kind of relationship. They would all look very different from each other. Some of them would be really small and others would be incredibly huge, but they all have the same kind of structural relationship. As many carbons as you had, you'd know you'd have exactly the same number, 4 times as many of that as hydrogens. So they're all kind of related. They all have the basic same ratio, and they show the same relative amount of atoms. Each one of them could then be simplified to show 1 carbon to 4 H's. Just like you saw yesterday with the diagrams in your POGIL, where you had the same kind of repeating units, but they could be simplified down. Sometimes that's really all we care about. What's the basic ratio of these things? How many hydrogens do we have compared to the number of carbons? How many carbons do we have compared to the number of H's? Sometimes we actually do want to know exactly what a molecule looks like. Does it have 2 carbons and 4 H's, or does it have 7,000 carbons and 28,000 H's? Is it a small molecule or a huge molecule? But other times we just want to know the more general information, like what is the most simple ratio of the elements in this molecule. Now, if we really do want to have actual complete information about a real molecule, we can use something called a molecular formula. And it's exactly what the name implies. The molecular formula is just the formula of a molecule. So some of the formulas we've seen in class, like H2O, CO2, O2, NaCl, things like that, they tell us the exact recipe for what a molecule is going to look like. If we want to talk about water, like I said the other day, H2O tells you what water looks like. If it doesn't have 2 hydrogens and 1 oxygen, it's not water. That's the molecular formula. Like I said, the name tells exactly what it describes. It's the actual formula of a molecule. So something like sugar, glucose we mentioned the other day, C6H12O6. That means if you wanted to build a sugar molecule, whether in a model or if we could actually put the atoms together piece by piece, you would need to have 6 carbons, 12 hydrogens, and 6 oxygens. That's the actual formula you need. That's the recipe. It has to look like that or it's not glucose. Hydrogen peroxide you may see in a pharmacy or on your kitchen cabinet or a bathroom cabinet. It has 2 hydrogens and 2 oxygens, a 1-to-1 ratio, but 2 of each one. It looks kind of similar to water, but you definitely don't want to drink this stuff. It's 2 hydrogens and 2 oxygens compared to water that has 2 hydrogens and 1 oxygen. So molecular formula tells you the actual number, the recipe of whatever this molecule looks like. Sometimes we don't really care about that. Sometimes we, like yesterday, just really care about the simplest equation. We just want to know the basic ratio of these things. We don't want to actually build these molecules and make sugar or make hydrogen peroxide. We just want to get a general sense of what they look like, how these elements compare to each other, number-wise. So we just want to know the ratio of these things. And that's where we can actually use these things like the reduced equations as we saw with the fractions. So how many H's for each oxygen? How many carbons compared to the number of H's? How many carbons compared to the number of oxygens? We can do that. We could look for these common numbers. So we could look at the sugar and see that there's a 6 here, there's a 6 here, there's a 12 here. 6 goes into all those numbers. We could look at the H2O2 and see that each one of them has a 2. Well, okay, in that case, the common number is 2. If we actually take these numbers out, then we could simplify these numbers too. Any guesses? 6 is 2s. We could simplify it to CH2O. We took a 6 out of each one, so we divide the 6 by itself, and we get a 1 for the C. We divide the 12 H's by 6, and we get a 2. And we divide the 6 oxygens by itself again, and we get a 1 for the O. Same thing with H2O2. We take the 2's out, and it reduces to 1 H and 1 O. All we care about in this case is the ratio. We don't care about what the actual molecule looks like. We just want to have a general sense of how these amounts compare to each other, and that's what an empirical formula tells us. It's just a reduced form. It's not what the actual molecule looks like. So obviously CH2O is not what sugar looks like. It's not what this glucose looks like. But it's okay. These two formula types serve different purposes. One tells us how we're actually going to make it, what it's actually looking like, and the other just gives us some general ratio information. In this example down here now, C2H8, we can look at this and say, well, C2H8 is a molecule. It's got 2 carbons, 8 hydrogens. But if we really just want to get a general sense of what it looks like, we can reduce it. We can get an empirical formula by looking for common numbers. And in this case, we see that the 2 and the 8, what number goes into them? Like I said before, always look for one of these numbers. See if they count as the number that goes into it. Well, I can see very easily that 2 goes into both itself and into 8. So if I take the 2's out, 2 divided by 2 gives us C with a 1. I'm going to leave it by itself. You could write a little 1 here, but usually you see it by itself. And if we take 2's out of H's, the 8 H's rather, 8 divided by 2 gives us H4. So that would be my empirical formula. The actual molecule would look like C2H8, but the empirical formula of it, the simplified version, just to give us a general sense, would be CH4. On the other side, NH4, let's try to simplify that. We have this molecule, it's called ammonium, NH4. But if we want to get just a general sense of the ratio of these elements, can we take anything out of here? Can we reduce it anymore? Does any number go into both 1 and 4? And no, the only number that does that is 1, and dividing by 1 is just going to give you the exact same number as again. So this already is an empirical formula. It is a molecular formula because this is what the molecule looks like. You can have a molecule with NH4, 1 nitrogen and 4 hydrogens, but it already is its own empirical formula. You can't simplify this anymore. So this is the empirical formula also. It's that small, it's that simplified, and we can't do it any better than that. So I basically said everything I want to say in this slide and the last one already. I'm not sure why that big H2O just popped up at the bottom of the screen. It's animated poorly. But like I said, sometimes a molecule is a larger version of its empirical formula. So when we look at the glucose molecule, the sugar, where it's C6H12O6, it's just 6 times larger than its empirical formula. It's showing this basic ratio in the empirical formula, but you can have an infinite number of actual molecules that all have a simplified empirical formula ratio of CH2O. It can be something that actually is CH2O. It could be one that's C2H4O2, because C3H6O3. You can go on forever. The molecular formula can be a larger multiple version of whatever the simplified formula is. You could also have things, though, where the molecule is its own empirical formula, like I showed with the NH4. There is a molecule that has the formula of NH4, 1 nitrogen and 4 hydrogens, but it's also its own empirical formula. You can't simplify it anymore. And water is probably the best example of this. Water, obviously, as you know, is H2O. There are 2 hydrogens, 1 oxygen. That is what the molecule actually looks like, but it's also the simplest version because you can't simplify those numbers. You can't take any number out of the 2 H's and the 1 oxygen and get it to be anything simpler. That is what it is already. And yeah, water, we know you're cool. We know you're really universally important for life, but that doesn't matter. You don't have to rub it in like that. Just quick information drop here. We don't yet know what ionic compounds are, and we'll go into that in more detail in future chapters. But when oppositely charged ions attract and make compounds, so when a positively charged thing and a negatively charged thing attract and make a neutral compound, like you saw in the POGO yesterday with sodium chloride, it had the positive sodium, negative chlorine, or the silver oxide, where it was a positively charged silver, I think it was, and the negatively charged oxygen, the formulas are always going to be written as the simplest ratio of the elements. So it was NaCl, 1 sodium, 1 chlorine, and not, I think it was, 10 sodiums and 10 chlorines or something like that. This is because you could technically just keep adding these things onto each other, 1 sodium, 1 chlorine, another sodium, another chlorine, on, and make these bigger and bigger molecules into infinity with these repeating units. Like if you had a large salt crystal compared to a small salt crystal, there's no point in counting, is it 10,000 these things or 5? All you care about is that there's 1 sodium for every chlorine. There were, 2 silvers for every 3 oxygens. You just care about that simplest empirical ratio, empirical formula. So when you're talking about these ionic compounds, it's always going to be the empirical formulas you're talking about. And again, these empirical formulas always show these related kind of relationships. So all of these guys over here all have the same empirical formula. Everything over here has the same empirical formula, and they're all kind of related to each other just structurally because they all can be reduced to that one basic ratio of 1 carbon and 4 hydrogens, or in the other case, 1 nitrogen and 3 oxygens. This page here, we're just going to try to identify what type of formula we have. Is it molecular? Is it empirical? If you look at a formula and the numbers in it could be reduced, it's molecular. It's telling you the exact recipe for that molecule for that formula. If the numbers are already reduced and you can't reduce it any further, you can't simplify it anymore, then that's empirical. It's showing you the basic ratio. So for this first one, C6H12O6, we looked at that before. That was glucose. That was our sugar molecule. 6, 12, and 6, we could still reduce that number. So this is not an empirical formula. It's telling us the exact recipe of something. So as you saw before, we could take a 6 out of here, a 6 out of here, and a 6 out of here, and reduce that down to CH2O. CH2O would be our empirical formula. That would be a simple ratio of these elements. For NH3, 1 nitrogen and 3 hydrogens. We can't reduce that anymore. That's already as simple as it would be. There is a molecule that's made up of 1 nitrogen and 3 hydrogens. That's what ammonia looks like. The cleaning product ammonia is that, NH3. So it is its own molecule, but it's simplified already, so we would say this is the empirical formula. For the next one, C6H16. Again, we just want to look at, can we take these numbers and use them? The 6 and the 16. What goes into both these? 6 does not go into each one evenly, so we can't do that in this case as we could up top. But I would look at this and say, well, they're both even numbers, so I know that 2 goes into each of them. So 6 divided by 2, we can make that C3, and H divided by 2, we can make that H8 as a simplified empirical formula. Don't be happy with one time. Let's see, can we do it again? Does any number go into 3 and 8? In this case, no. So it is going to be where we stop there. This was a molecular formula to start, but we reduced it to an empirical formula. It says up here, if it's molecular, reduce it as much as you can to make it empirical. Just keep in mind, you have to be able to reduce each number the same way. We can't look at a number and say, well, we could take 2 out of here and a 2 out of there, but the other number is 5. It has to be able to reduce everything the exact same way, or you can't do it. You have to leave it alone. So go complete the rest of these, and I'll see you on the next slide. The last thing we're going to talk about here is what's called formula mass, or gram formula mass. You may sometimes hear it referred to. There is a difference between those two terms, but we'll see that in a different chapter. It's going to be really not any more complicated, just what terminology do you use. But formula mass is exactly what the name says. Just like before, where the molecular formula was the formula of the molecule, the formula mass is just the mass of the formula. So find a formula, see what it's telling your molecule looks like. We have H2O written there, we see CO2 written, and I see KMNO4 written. The formula mass is just the mass of that formula. How much does the whole thing weigh, essentially? How much does a molecule of water weigh? How much does a molecule of carbon dioxide weigh? How much does this molecule of potassium permanganate weigh? So our reference tables don't tell us how much different molecules weigh as whole, but they do tell us how much the individual atoms that make up those molecules weigh. Each atom has a weight or a mass based on how many protons and neutrons are in its nucleus, if you remember from the atomic chemistry chapter. Those particles give it mass, and that mass is listed on each little periodic table tile, as I gave you on the right side of the slide here, where it is the atomic mass. So right up here. And if you remember from previous chapters, we always will round that number off. So for 1.00794, we're just going to round that down to 1. For carbon's 12.011, we round down to 12. For oxygen, it's 15.9994. We don't want to use that number. We're just going to round it up to 16, and things like that. But that is our atomic mass number. And if we know what each atom weighs, well, then we just have to go add it up. So as it says here, we're going to count up our atoms, and we're going to remember the subscripts are there. So if we want to find out how much water weighs as a whole molecule, we just have to find out how much each hydrogen weighs. And when I say find out, we just go look it up. It's on a reference table. And then we'd also add up how much that one atom of oxygen weighs. If we know water is made up of 2 hydrogen atoms and 1 oxygen atom, we just need to find out how much each hydrogen and each oxygen weighs, add them all together, and remember that the subscripts do tell us the number of these atoms. So we can't just say for carbon dioxide, for example, that there's 1 carbon and 1 oxygen and add that up. We have to take into account that there are 2 of those oxygens and make sure we add it that way. Now, these 3 examples are not in your notes. I gave you a couple more to do in a second, but I just wanted to start out with them because they're smaller and they're easier, and I want to make sure I actually give you the numbers and the pictures over here. So keep it quick and simple. For water, we're going to look at it, and here's how I'm going to do it. I'm going to write it the same way I do it every time. And as I've said in the past, I suggest you just do this to start out until you get maybe more familiar with and more comfortable. Then you can do it however you want to. But I'm just going to give you kind of a set way to do it where I'm going to repeat it. And just make sure you show any work like this on a quiz, on a test, anything, so I can follow your process, because it's really easy to screw this up if you don't kind of keep yourself organized. So I'm going to just draw some lines here so I can keep these things separate. And then for water, I would say for myself, I have hydrogens, and I have, that's not a dot, I have hydrogens and I have oxygens. So for hydrogens, I see there's a little 2, so I'm going to say there's 2 of them. And if I look now up at my little thing up here, I see that each hydrogen has a mass of 1. So 2 hydrogens, each one weighs 1. My total mass from the hydrogen parts is 2 atomic mass units. That's the combination of protons and neutrons for each atom of hydrogen. For oxygen, I'm going to do the same thing. I can see that I have 1 atom of oxygen, and I'm going to go to my reference table and see that each atom of oxygen weighs 16. The combination of protons and neutrons is 16, so each oxygen atom weighs 16 atomic mass units. So doing my math over here, my 1 atom of oxygen times the 16 that each oxygen atom weighs means that that 1 atom of oxygen weighs 16. And now I just want to add that up. So my 2 hydrogens altogether weigh 2. My 1 oxygen weighs 16. So adding it up, I can get 2 plus 16 tells me that my water molecule weighs 18. I'm going to write AMU for atomic mass units, but the units are really not important right now. Each water molecule weighs 18. Do the exact same thing for carbon dioxide. For carbons, I have 1 carbon. I'm going to look over here and see that each carbon atom weighs 12. So 1 times 12. The mass of my 1 single carbon atom is 12 atomic mass units. I have oxygen also in this molecule. I have, in this case now, 2 oxygens. Each oxygen, as we just saw before, weighs 16. So altogether, my 2 oxygen atoms weigh 32 atomic mass units. I'm going to add those 2 up now. And these 2 elements now, my carbons were 12, my oxygens were 32. And if I add all of them up together, 12 plus 32 equals 44 atomic mass units. So every molecule of carbon dioxide weighs 44 atomic mass units. Not too bad, right? Bigger one is a tougher example, but do the exact same thing. It's repeating the same exact process over and over again. This is called potassium permanganate. If any of your friends are in research, or if you are in research, I don't think any of you are, but if you are, you're probably familiar with this because the research kids love to talk about this. They think it looks really cool. I disagree because there are many other cooler looking compounds, but they like it because it has a cool purple color. Potassium. There's 1 K in this molecule. I can look on the reference table and find that the mass of a potassium atom is 39. I'm rounding it off. So 1 times 39 is going to give us 39. Manganese, Mn. Notice as we were talking about the other day, you have a uppercase letter and a lowercase letter. That tells us it's 1 element. Once you see a bigger letter again, you know it's a new element. In this case, Mn are 1 element. I see there's only 1 of the manganese, so I write 1. The reference table tells us that each atom of manganese weighs 55. We're rounding off 54.9 to 55. So the mass of just that is going to be 55. And for our last elements, the oxygen, there are 4 oxygens. Each one, as we saw before, weighs 16. So that's going to give us a total oxygen mass of 64. Now we have to actually add these up. And I did not take my calculator out, so I'm not even going to bother to try to do this in my head, but add up 39, 55, and 64, and that'll tell you what the total mass of potassium permanganate is. These examples I actually did give you your notes because these are the ones we normally do in class. I just decided to add those 3 for now because I want to be able to explain on video. Do the exact same thing. We just did 3 together. Now do these 6 on your own. Some of them are tougher, some of them are easier, but it's the same process every single time. When I say tougher, I really just mean it's a larger molecule. For this one, nitrogen, I'll do the exact same thing. Nitrogen, there's 1 of it. If I look up nitrogen, I'd find it weighs 14. For hydrogen, there's 3 of the hydrogens. Each of them weighs 1. So 14 from the nitrogens, 3 from the hydrogens, add it all up, the whole thing weighs 17 AMUs. Do the exact same thing for the next 5 examples, and that's it. This is kind of a challenging question I gave you just to see if you could bother with it. I was more concerned with what your thought process was trying to figure out how you could answer this question than if you actually could, because I really don't expect you to be able to do it. This is a more complicated one. It's something we'll get to eventually, but because this video is already almost 20 minutes long, as I've skipped it this long, I'll go back to it. I'm going to just skip it. There's no point in doing this now. We'll get to it at some point in the future. It is now, as I look at the clock, 2:37 p.m. on Saturday. I know I said I was going to try to get this up by midday, so you knew to do it or not. It took longer than I thought to record this and get everything ready, so I know this is already running a little long. But for now, you're done with the video. Just go through now, and I'm going to give you a couple of forms questions. It should be below this on your OneNote page. I just have to actually load up now, and I'm going to get, after I give you this YouTube link, I'm giving you, I think, 2 comprehension questions, basically like reading comprehension, except it's from a video, obviously, just to see, did you get the point of all this? And then I think I'm probably giving you 2 more application questions. So using the actual skills we talked about here. Can you go back and add these numbers up to figure out how much your molecule weighs? Can you figure out is something a molecular formula or an empirical formula? So applying this new knowledge. The last question is a fill in the blank question. I want you to tell me something you don't understand. If there's 5 things you don't understand, hopefully that's not the case, but write it all out. I'm going to make it a big field so you can write whatever you want. I'm looking for questions that I can answer for you on Monday. Don't just sit here and say, oh yeah, it's all good, and then just ignore anything you're having trouble with. Tell me what you want me to go over, because I don't want to have to go over this whole thing on Monday. That's the point of the video. I want to address exactly what you want to talk about and what you need to have me explain in more detail. Monday coming in, 5-minute quiz, 3 to 5 questions, quick, boom, 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 get these answers out. You should have practiced with it by then. Molecular versus empirical formulas. Can you calculate a molecule's weight? You have your reference table, have a calculator, do it quick. We're done, and then we'll move on. We'll do some practice, and we're actually then going to go back and do a little bit of bio.